I meant to record since we are missing some people. So I'm starting late. Okay. I wanted to show you guys, there's a program listed there on the page, and I wanted to show you guys that program. It's kind of fun to play with. Where did it go? Did I? Yeah, there it is. So this is a slope field generator. So like we just did the function 2x, and obviously it can calculate a whole lot more for us. We're seeing all the slopes of 0 right on the y-axis, slope of 2, 4, 6, 8, you know, they're getting awful steep. I'm not sure why, but you can move this point around if you want to. If you had 2x plus y, there's the slope field. So this is kind of fun to play with, I think, and if you're wondering if your slope field looks right. Okay, so if you were to say you knew that this was a solution on your graph, then it looks like the function would go up steeply here, hit 0 here, and go up kind of steep that way, if that sort of makes sense. What you try to do is sort of visualize a function that would go through this point and would have these lines as tangent lines. So that's kind of fun to play with. All right. Go back to this. Okay. Sketch the slope field for the differential equation y prime equals x plus y, then sketch in a particular solution if y of 0 equals 1. All right, so what would the slope be at the point 0, 0? Jillian?
Wouldn't it just be, would it be 1?
At the,
or no, that's the,
at the point 0, 0, so y prime equals x plus y. So if the point is 0, 0, the slope is
0.
It's just 0. Does that make sense?
Yeah.
Okay, so right here, I know, kind of hard to see because of the line here. Moving over here to 1, 0, the slope would be 1. You just add the x and y coordinate. And again, try to make it kind of have the right slope. At 1, 1, the slope would be 2. At 1, 2, it'd be 3. At 1, 3, it'd be 4. So it's getting a little steeper here. At 1, negative 1, it would be 0. At 1, negative 2, it'd be negative 1. At 1, negative 3, it'd be negative 2. At 2, 0, it would be 2. 2, 1, it'd be 3. Then it'd be 4. Then it'd be 5. 2, negative 1 would be 1. 2, negative 2 would be 0. 2, negative 3 would be negative 1. And we just continue. Now, on the AP exam, I think they limit the number of points. You wouldn't have this many points that you would be doing. But I think we can see at 3, negative 3 would be 0, 2, negative 2, 1, negative 1, negative 1, 1, negative 2, 2. So we're going to have, on that diagonal line, they would all be 0. At 2, negative 1, it was 1. Let's see. 3, 0 would be 3. So we would just kind of continue and get a whole bunch of points. Says, when does the solution to this differential equation have a slope of 0? I kind of just talked about that. It's when x plus y equals 0, so y is the opposite of x. So that's along that diagonal line. That's when it would be 0. Questions so far, guys? Is this making sense?
How would you plot the specific point?
Say that again.
How would you plot the specific point? They gave you y at 0 equals 1.
Oh, then sketch the particular solution if y of 0 is 1. Okay, so that means we're looking at the point 0, 1, right? And let's see, the slope there, I probably should do that point, would be 1. And so, and at 2, 0 would be 2, and it'd be 3. And at -1, 0 would be -1. So I know everywhere along this diagonal line, it would be, the slope would be 0. So I would say, it looks like the slopes are going like this. It's going to bottom out somewhere around here. And then -2, 1 would be -1. -3, 1 would be -2. So probably, yeah. And then it looks like it kind of would do something like that. It's easier the more points you have. So if we look at the next, sometimes they give you like a bunch of points and then you just fill in the slope. It's just kind of a, hey, let's look at it and see what would sort of fit. It's not a real precise thing at all, if that makes sense. All right, match the following equations to their slope field. I'm gonna give you guys a minute to do this.
So could this be, could you find this by saying what the slope of each of these lines changes with? So like, with if it changes as it goes along the x-axis, could you say that that would be the one that would involve x? Or would that be?
I think you're on the right track there, George. So yeah, let's go ahead and think about this. So when you say like this one, dy dx, it involves x, and y is not there, right? Like the derivative is dependent only on x. Is that what you're saying?
I think so.
Okay. So that means that when x is like 1, it doesn't matter what y is. Everywhere where x is 1, it should have the same slope. Does that make sense?
Mm-hmm.
So is that happening in which one of these 3 graphs? If you look as, if we look sort of up and down, like pick x equals 1, do these all have the same slope? Well, yes, they do. Here when no, they don't, they change. Here they do all have the same slope, but the slope is the same everywhere. So this very last one, the slope is the same everywhere. It doesn't change at all. So which one of these 3 functions or equations does that go with? What do you think, George?
I think the first one.
Yeah, exactly.
The slope's always 2.
The slope is always 2. And then of these 2, which one would be the 2x? The The A or the B?
Oh, the 2x. I think that would vary based on x, so it would be A.
Yeah. Right. Because it's only based on x, y doesn't matter. So if you look up and down a line where x is constant, hey, they're all the same. Here, if you look across, so where y is a constant, all the slopes are the same. The derivative depends only on y. Yep. All right. Slope field for a differential equation is shown below. The function y is the solution to this differential equation. Determine which of the following statements are true. The function y is always concave down. So if you imagine picking a point and sketching in a solution, does it look like wherever you pick a point, the function would be concave down? What do you think, Stella? Can't hear you, Stella.
Yeah, it would be concave down.
Okay, does that make sense to other people? Yes, so that's going to be true. The function y is increasing where x is greater than 0. So again, if I look on this side, x is greater than 0, does it look like the function's going to be increasing? Austin's shaking his head no. I would agree. Definitely looks like it's going to be decreasing. The function y is a constant function. If it's a constant function, what would the tangents be?
Would they all be the same constant? Right?
Well,
Oh wait, no, they would all be like this, like that constant times a number, right? They would be
the function's a constant, like something like y equals 3. What's its derivative?
3x.
dy dx would be,
I was integrating it.
okay. What would be the derivative of 3? 0, right? So if the function is a constant function, then the derivative's always 0. I would have a whole bunch of horizontal tangent lines. So that's false. The function y is a linear function. If y was a linear function like 5x plus 2, the derivative would be something like 5. It would be just a constant. So the slope would be the same everywhere. Well, that's not the case. The slope is changing. It's not always 5. So that would be false. The differential equation only has x in the equation. Y is not in it. What do we think about that? Grace?
I would say yes, because at like x equals 0, it's just a horizontal line.
Right. So if you look here where x is 1, they all have the same slope. When x is 2, they all have the same slope. X equals 3. So that's true. Y would not appear in the equation. The function y is even. That means the function would have symmetry about the y-axis. Austin, what do you think about that? Does it look like any equation we draw in would be even?
Yeah, true.
Yeah, these two sides are, what's the word? Mirror images of each other. The function y has a horizontal tangent at x equals 0. So whatever the y value is, if you look at x equals 0, we see a slope of 0. So that means there would be a horizontal tangent there. All right, sketch in a solution if y of 0 is 2. So I plot the point 0, 2, which is right here. And following the guidelines of these slopes, it looks something like that. So what type of function does y appear to be? One of our favorites, guys. Everybody at once. What is it?
Exponential.
X squared, negative x squared.
A quadratic of some form. Exactly. A parabola. Okay. All right. So here's a fun slope field. So this is the y prime equals x cosine of pi y. So this is a fancy one. It's shown in the figure. This is one where you want to use a slope field generator, your computer, in other words, not by doing it by hand because this would take forever. Sketch the graphs of the solutions that satisfy the given initial conditions. Y of 0 is 0. So at the origin, right here, it looks like if I follow the general lines, it looks something like that. Because because I have a row of horizontal tangent lines here, it looks like I've got an asymptote thing going on. Okay, so that would be y of 0 is 0. Y of 0 equals 0. Y of 0 equals 0.5. So the point 0, 0.5, well, that looks like, if I draw something to match those lines, that looks like that's just a constant function. Y of 0 is 1. Okay, well, it looks like it goes down, and it looks like I would be hitting a tangent line. Y of 0 is 1.6. That would be up here. Oh, that looks kind of like that. So, kind of the moral of the story here is, I said how there wasn't just one solution to a differential equation. The example I gave you, just the plus c change, so it would move up or down. But what we're seeing here is that they can be very different types of functions. I've got a constant function. I have this thing which has an asymptote. This which has a horizontal asymptote. This is most assuredly not an x squared, but it's a curve. It's kind of that shape, a U shape. So solutions to a differential equation can be different types of functions. Okay. Are we okay so far? Questions for me? Questions?
Would you be able to go back to the second page? I just didn't get the very last part
Yeah.
about sketching. Oh, it was just sketching it in. Okay, never mind. Thank you.
Yep. Okay. All right, so hopefully you know how to plot points to create a slope field. And I think it's, again, it's a way to visualize solutions to differential equations. Our next lesson will be working at how to actually find some solutions to what's called separable differential equations. One of the things that you could be asked to do on the AP exam is to verify solutions for differential equations. We did, on the first page, we did 2 of those, verify solutions to differential equations. But this was on the you know, the AP, the College Board is having those two teachers do weekly lessons, and their second lesson was on verifying solutions, and they put together these problems from the AP classroom of verifying solutions. So I think they're worth doing. I thought we'd do a couple together, and I'm gonna ask you to do the rest as part of your homework. So the function is a solution to which of the following differential equations? Oh, that's fun. You're not just asked to verify, you've got to figure out which differential equation it's going to work in. So notice there's a first and a second derivative in the differential equation. So I would take this and I would figure out what y prime is. So e to the 3x, it'd be 3e to the 3x minus 5. And y double prime would be 9e to the 3x. And then the derivative of the 5 is just 0. All right. So I got to kind of guess and think about which one I think this might work in. If I take just y double prime, I might start with one of these C and D because they seem like the easiest. So if I start with, say, D, y double prime is 9e to the 3x minus y prime plus 5. Notice y in this one isn't even in the equation, just y double prime and y prime. 9e to the 3x minus 3e to the 3x would be 6e to the 3x. And I'd have plus 5, which is plus 10. That's not working at all, right? Do you see why that means that C probably isn't going to work either? Because the only difference there is subtract 5 instead of add 5. So that's not going to work. So it looks like it's either A or B. So I'm going to need to multiply that y prime by 3, and I'm either going to add or subtract 15. So let's try A essentially. The second derivative is 9e to the 3x. 3 times the first derivative, 3e to the 3x minus 5. And then it's either going to be plus or minus 15. I just need to figure out which one. So 9e to the 3x minus 9e to the 3x plus 15, because negative 3 times negative 5 minus 15. Looks like I picked the right one. That's 0, that's 0. So A is my solution. Questions so far? So here we're given the differential equation and we're told an initial condition, and we're asked to say, figure out which one of these functions would be the y function. I would start with the initial condition and see if I can eliminate any possibilities based on that. So like 0, 5, okay? Well, tangent of 0 is 0. E to the 0 is 1. 1 plus 4 is 5. So I cannot eliminate that one. Tangent of 0 is 0. E to the 0 is 1. Plus 5 would be 6. So I can eliminate option B. Tangent to the 0 is 0. E to the 0 is 1 times 5 is 5. So the initial condition works there. Tangent of 0 is 0. 0 plus 5. That works. Tangent of 0 is 0. 5 times e to the 0 would be, so that'd be 0 plus 5. That works. So we're only able to eliminate one of the solutions using the initial condition. Okay, so it's saying that the derivative of the function is equal to the function itself times secant squared. We think about that. Which one of these, do we have an idea? When I take its derivative, it'll be the function itself times secant squared. let's try just A maybe. So if y equals e to the tangent of x plus 4. So y prime, the derivative of e to the tangent of x. Adam, what would that be?
Would that be secant squared x e to the tan x?
Exactly. And then the derivative of the 4 is just 0. So again, I'm looking for the function itself just times secant squared. Well, that's not what I have. The function itself is an e to the tangent x, it's e to the tangent x plus 4, but the 4 went away when I took the derivative. So A is not right. Anybody want to make a guess? Which one do you think we should try next, C, D, or E?
C.
What was that?
C.
B's not going to work. Did you say B?
No, I said C. 5e to the tan x.
All right, so let's say, what if this is 5e to the tangent x, then y prime, you do 5e to the tangent x times the derivative of the tangent, which is secant squared x. So there's my y times secant squared. Okay, so thinking about this as the function itself times secant squared, here I know when I take the derivative, I'd be losing that 5. Yeah, it's just, so it's C.
Miss Armato? Yeah. How did the 5e to the tan x turn into y?
We said that we're asking, does y equal 5e to the tan x?
Okay, okay.
So I'm pointing out here that once I took its derivative, look, I had the function itself, 5e to the tan x
Okay.
is times the secant squared. Does that make sense?
Okay. Yeah, that makes sense.
Okay. Let's look at problem 3. So I'm gonna, yeah, we've got what, 5 more minutes. And then again, I'm gonna ask you guys to work on the rest of these. If you want to see them doing more examples, you can watch the second video that they did, that I've sent you the link to. They went through this. This is what they did for 45 minutes, was they went through all of this, or most of it. A curve has slope 2x plus 3 at each point xy on the curve. Which of the following is an equation for this curve if it passes through the point 1, 2? So first of all, that's an initial condition. 1, 2 has to be a solution. So I would start by plugging in 1. 5 minus 3 is 2. That's an option. 1 squared plus 1 is 2. That's an option. 1 squared plus 3. Oh, 1 squared plus 3 times 2. No, 1 squared plus 3. God, I can't do work. Is not 2. So I can eliminate that one. 1 plus 3 is 4 minus 2 is 2. That works. 1 squared is 1, so 2 plus 3 is 5. 5 minus 3 is 2. So again, I'm only able to eliminate one solution using that initial condition. Now a curve has slope 2x plus 3. How do I write that in calculus language? What do we think?
Y prime is 2x plus 3.
Exactly. So that's giving you your differential equation. Okay, well this one's pretty simple because it only has x in here. So if y prime equals 2x plus 3, which of these functions can be y? I mean, when you take the derivative of this, do you get 2x plus 3? No. Here you get just 2x. How about D? You would get 2x plus 3. On E, you would get 4x plus 3. So this is the answer. So it might have been easier on this one to ignore the initial condition and just be like, oh, the derivative is 2x plus 3, you know, because that's a fairly simple derivative. What time is it? Oh, it is 9:30. Okay. So I will tell you, number 2's probably the most challenging one on here. So you might want to save that one for last. But I'm asking you to work through the 7-4 homework, which I gave you, and the rest of the problems on here. And again, if you feel like you want more on this, you can look at the video on the College Board website. And don't forget to do your take-home quiz. Awful lot of you are up to 40 questions on the Delta Math, but a few of you are not. Please keep working at it. Let me know if you need some help. But I do want you to get up to 40. I've put in the grade book missings if you weren't up to 20, which means it counts as a 0. Grades are being pulled at noon today. I am not putting in missings if you aren't up to 40 yet, because I didn't want that to like hurt you at this point. But you do need to get up to 40 questions for your score. All right, questions?
Nada,
Yeah.
You might have said this, but sorry, you cut out. Is the 7.4 and the differential equations both homework for Wednesday?
Yes. So.
Okay.
Yes. I want you to finish
Okay, sounds good.
and do my homework, the 7-4 homework.
Okay, thank you.
Yeah, I think this is really valuable. Okay. Anything?
Have you emailed this worksheet out, or where can we find it?
I emailed it out and it's on the Haiku page.
All right.
Yeah. Yep. All right. If anybody wants to hang on, you know, and talk to me one-on-one, that's fine. I'll stay on for a minute. But you guys have a great Monday, and don't forget to send me your quiz.
Thank you.
Thank you.
Thank you. Bye.
Bye.
Thank you.